problems. Yeah. Thank you for the introduction, and thank you, Oripa, for the invitation. It's a great honor to participate to this Power to X workshop program. So I'm the first speaker, and my name is Laisuo. I'm from the University of Texas in Dallas. So I'm assistant professor in the Department of Material Science and Engineering. So my topic today is sodium halide solid electrolyte with high ionic conductivity. So before going to the research talk, I want to have a brief introduction about our school and our department. So UT Dallas is one of the 13 universities in the University of Texas system, and we are ranked just under the UT Austin, which is the flagship university in the UT system. So we are classified as the R1, which means a very high risk active, and our school is very strong in STEAM, STEM education, and we're also a very young university, only like 50, 60 years compared to other universities. We usually have hundreds of years of history. And our department has the highest funding per faculty in the School of Engineering. And we also have the state of the art. So this is a picture of our department and looks very, very beautiful. And we have the state of the art facility and the dry rooms. And in our school, university, we have 3 centers, and 2 of them are within our department. And here Beacons is our battery center, which is we received the 13 million funding from the Department of Defense to build this center to fabricate some power cell and synthetic cell. And our department focused on semiconductor and energy materials. So about my group, so we are doing solid state electrolyte study and liquid electrolyte using a technique like machine learning and the data-driven method. We also study batteries in the drone and robot applications. So here's our group photo taken during the summer group lunch. Okay, so here is an outline of our current topic. So I will give a very brief motivation of why studying sodium solid state electrolyte, and then go to the challenge and a solution, and then we'll have a brief conclusion. So here are the 2 manuscripts published that's relevant in this talk. So first of all, so compared to lithium, sodium is more abundant and cheaper. So here is some market price of lithium carbonate and sodium carbonate. So for lithium carbonate in 2025 in the United States is 11,000 per ton, and the sodium carbonate is 5 times cheaper compared to lithium carbonate. If we compare to the crust abundance, sodium is the number 5 among all the elements. The lithium is very little. So this is one reason of selecting sodium batteries compared to the state-of-the-art lithium-ion batteries. So here is the table to compare lithium and sodium. They have a very similar properties, but a few difference is sodium is heavier than lithium, and the sodium ion is larger. Sodium is not compatible with graphite, so usually hard carbon is used. And theoretical capacity of sodium anode is less than lithium. And so despite those disadvantages, but sodium has a lot of similar properties as lithium. So lithium ion facilities can be used directly to fabricate sodium ion batteries. So if we want to compete with the lithium ion batteries, we have to use some solid state electrolyte to replace the liquid electrolyte. In this case, we can use sodium metal, even anode-free. By doing this, the cell level energy density can go to 200 to 300 watt-hours per kilogram. So by using this, we can use the sodium solid state batteries with some even for electric vehicles. And here is some Huawei new energy battery makers. They have some demonstration using sodium oscillator batteries for electric vehicles. And here is to develop solid state batteries, we have to develop a solid electrolyte, which is the key for developing solid state batteries. And compared to other oxides like sulfide, halide batteries have good oxidative stability, facial productivity, and good thermal stability and good interfacial affinity. The limitation of halide is its low ionic conductivity and poor reductive stability. So in this work, we are trying to solve the low ionic conductivity issues for halide. And there's one more comparison of sodium halide electrolyte with its lithium counterpart. so lithium yttrium chloride, lithium indium chloride, and lithium zirconium chloride, which have three common halides. Their lithium counterpart has a conductivity close to 1 millisiemens per centimeter, but their sodium counterpart is much less, 0.001 millisiemens, even at high temperature. And the reason is for two aspects. The first one is sodium is much bigger. The second one is hard to synthesize sodium halide with the desired structure. And here are some examples of the halide. They are all hexagonal close packed or cubic close packed. So those examples are all based on the close packed anion structure. So in 2000, let me go to the outline to the solutions. So in 2023, there's a paper published in Nature. So they developed a first non-close packing anion structure, lithium chloride. So this is lithium chloride, a non-closing close packed structure, have a large 1D channel for ion transport. So they report a lithium chloride and can achieve a high conductivity and good compatibility with lithium metal. So built on this work, we're trying to replace the lithium with sodium. So try to develop a sodium lithium chloride. So this is sodium lithium chloride. If you write them in the sodium 0.5 and the sodium 0.25, lithium 0.75, and chlorine 3. So this part is the lithium chloride, which means 25% of lithium is replaced by sodium, and the rest of 50% of sodium stays in the 1D channel. So this is our target crystal structure. So some sodium and lithium in the 2C site, and the rest of sodium stays in the 2B site, which is the 1D channel. So to achieve this composition, we used a solid state synthesis. So we have a stoichiometric ratio of sodium chloride and lithium chloride, and then we mix them, use a mortar, and then we center them at a high temperature, followed by ball mill. So here are our synthesized steps. So the first synthesized sodium lithium chloride has a very poor ionic conductivity, and here is the XRD and the different temperatures, and here is the XRD peaks, XRD pattern and the fitted peaks. The conductivity is 10 to the -9 Siemens per centimeter, which is very, very low at the room temperature, and we also have a high activation energy. So, and then we did a synchrotron XRD and do the refinement to figure out the reason. And we found there's some impurity peaks here. And after refinement, we find the sodium percentage in the 2B site. 2B site is the desired site we need. It's only 0.16, which is very little. So we want this number to be 0.5. And we also have some impurities here. So we didn't achieve the desired structure we need. So to solve this issue, we try to use a zirconium doping to replace the lithium. The reason is zirconium has a smaller radius. So compared to lithium, have a 103 picometer, zirconium is only 72 picometer. So this can extend the channel size to allow the sodium occupation. And the second, the zirconium 4+ has a larger valence compared to lithium. So this will introduce more sodium vacancy on the structure. So by using this, we tried different amount of zirconium doping from 0% to 30%. So the ionic conductivity is increased from 10 to the -9 to 10 to the -6 Siemens per centimeter. That's the highest we can achieve, but this is still not high enough for solid-state battery. So we first go back to the synchrotron XRD to study the structure. We found by using lithium zirconium doping, we can achieve the 2B site occupancy to 0.46, which is close to 0.5. So we kind of achieved the desired structure. And then we did one more step. So after the heat treatment, we did an additional ball milling. By doing this, so with the ball milling after centering, we're able to put more zirconium into the structure. And here we can see, and 30% of zirconium, there are still no impurities, but when we reach the 40%, we start to see some impurities. And ionic conductivity also gradually increase from 10 to the -9 to 10 to the -4. And here, So this is 2.9 times 10 to the negative 4 Siemens per centimeter. Is already high enough for solid-state sodium batteries, and the energy is also pretty low. So by doing this, we use this solid-state electrolyte, and we test the oxidative stability and the reductive stability. So this electrolyte can have a stable window from 1.33 to 0.8. We also test the symmetric seal, and it can stable up to 80 hours. And we made our batteries using the developed sodium lithium zirconium chloride. And here is the battery structure. And here's the red performance of the battery. So at 1C, the battery can still achieve around 90 mAh per gram. The red performance is pretty decent. And we also test the cycling stability of this battery. So it can last over 70 cycles. And the main reason for the capacity retention is coming from the impedance increase. So here's a quick summary for this first work. So we are using the down-closing ion structure and using the zirconium coating to expand the 1D channel. By doing this, we achieved a sodium halide-based solid-state electrolyte with ionic conductivity of 2.9 millisiemens, 2.9 times 10 to the power of 4 Siemens per centimeter. And then for the second work, we used anion doping to achieve amorphous structure. And this work is published in the Small this year. So the philosophy on the rationale coming from here, in the halide, when anion is different, they have a cation have a different structure. So when the anion is sulfide, the tetrahydroside usually have a lower energy compared to octahydroside. But when we replace the anion from sulfur to chlorine, then the tetrahydroside will have a high energy to octahydroside. When anion is oxygen, the tetrahydroside and octahydroside have a similar energy. So if we mixed the anion using mixed oxygen with the chlorine, we are thinking the energy difference between the tetrahydroside and the octahydroside can be reduced. This will reduce the energy landscape from different sites, which will enable fast ion transport. So we start from the sodium niobium chloride. So this is our benchmark material, and here is the structure. To achieve oxygen doping, we use the sodium hydroxide, and this is the reaction mechanism. The sodium hydroxide plus the niobium chloride, which will achieve the oxygen-doped sodium niobium chloride. And here is an XRD pattern of these two materials. So sodium niobium chloride have a good XRD pattern, peaks, which is a crystalline phase, but the oxygen-doped is an amorphous phase. And then we test the property. So the benchmarking material is 0.009 millisiemens per centimeter. By using different amount of doping, the best conductivity we can achieve is beyond 1 millisiemens per centimeter, which is over 100 times higher. And here's a comparison of our material with other halide material. Our material has a high ionic conductivity and low activated energy here. We also test the electronic conductivity. So this material is almost an electronic insulator, and here is lower than other halide. So it's the conductivity mainly coming from the ion movement. And we test the change of ionic conductivity versus temperature, and also the XRD at a different temperature. We found when we increase the annealing temperature, the ionic conductivity decrease and the XRD peaks increase. So this increased ionic conductivity can be correlated to the amorphous dominant crystal phase. And we did a machine learning-based DFT calculation to study the number of sites within the two structure and the energy difference among different sites. So compared to the baseline sodium niobium chloride, the oxygen doped have a higher number of sites for sodium ions and a smaller energy barrier for ion movement. So this is the reason for faster sodium ion transport. And then we used a similar structure to make sodium batteries. So this electrolyte is also stable in dry air for 24 hours. and shows decent rate performance and very good long-term cycling stability. So we cycled for 500 times, the capacity retention is still beyond 80%. So here's a quick summary from the second work. By using oxygen doping, we're able to achieve amorphous dominant phase with a high ionic conductivity, and DFT calculation shows the reason for the high mobility of sodium ions, and we fabricate cells that shows decent rate and cycling performance. So here is the main work for this talk, and I would like to acknowledge the funding source and all the contribution from our group. And thank you, everyone.
Okay. Thank you so much, Professor Su, for your wonderful talk and great insight on the solid state electrolyte for sodium ion battery. So the forum is now open for question. So if there is anyone who would like to ask question, please feel free to raise your hand.
I want to know this, how to make a cell without using sintering.
You mean how to make a all-solid batteries without sintering?
Yes, yes.
Oh, yeah. So for this halide, they have a good deformation capability. So when we make cells, we apply a high pressure, usually to 300 megapascal. So by doing this, we can reduce the porosity down to like less than 10% or even 5%, so that they have a good mechanical contact. So yeah, just apply a high pressure because they have good deformation capability. Does that answer your question?
Oh, no, thank you.
Okay, any more questions? Oh, please. In front here. Oh, no, the microphone is coming.
Thank you for your talk. When you simulate the effect of crystallinity on the conductivity, what is the crystal structure that you assume for this oxygen doped one?
So we didn't assume
from the chloride one, or
yes, that's a very good question actually. So for this simulation, we don't assume any crystal structure. So we start with a sodium niobium chloride, which is the hexagonal structure, and from here we replace the two chlorine with one oxygen, and we let the system to relax.
Okay.
And this is a small size simulation. So we only simulate the local environment, not a long-term crystal structure.
Okay, maybe you can try again. Actually, there is a crystalline phase of NaNbCl4O, but it has a structure, the orthorhombic structure of the close to the thallium niobium oxychloride. Mm-hmm. So and with that, but you get relatively low migration barriers, so that's rather consistent. So independent of this.
Great. Thank you for the advice.
So, thank you very much for a very good talk. But may I know the amorphous nature of your sample prepared, and also whether you measured the glass transition temperature of the electrolyte you prepared. When you doping takes place, how does the glass transition temperature decreases?
Are you talking about these nights? Huh? Oh. I'm sorry, I didn't get your question.
Okay, but what is the glass transition temperature of the material?
Oh, glass transition temperature. Okay, oh yeah. So I asking the glass transition temperature of this material. Okay. Yeah, we didn't do TGA and DSC for this material, okay. But from the I would say from the XRD, into XRD, yeah, maybe it's close to, I would say 150, between 150 and 130. but we didn't do the TGA for this material.
Okay, actually, I have quick question on this activation energy that you show on this slide.
This slide?
Yeah, so the number you write down over there is the activation energy, right? Or is
this is the conductivity.
It's the conductivity, sorry. So what is the activation energy that you get for this material?
It is 0.247 EV.
Is it agree well with the simulation result that you calculate?
And in the simulation, we didn't do the activation energy. This is the energy difference between the different sites. So in this structure, it has like 130 sites for sodium ion. And then we calculate the energy in the different sites, and we do a statistic analysis. And from here,
so you didn't calculate migration energy.
Right. Yeah.
Okay, thank you.
But it's a good point. Yeah, I think it's difficult, but it's worthwhile to try in the future. Yeah.
Okay. So, okay. One last question, please.
So, hi, Su Lily. Thank you again that you come for a talk today. It's really nice talk. Anyway, actually, I have a really simple questions and not really deep study thing. I have been talking with my friend in the solid state electrolytes that we talking about like what is the most main problem of the solid electrolyte, like ionic conductivity, tuning crystal structure, or the interface problem things, because now we also need to use the high pressure. So now today I just see you that focus deeply on the ionic conductivity and crystal structure. And then what do you think about in terms of the interface problem or even the contract problem in the solid electrolyte?
Yes, it's a very good question. I would say interface problem is one of the most important questions for solid state electrolyte. And actually, for the conductivity, the lithium solid state electrolyte is already meets the requirement for batteries, but the interface is the bottleneck here because they are solid contact and they're very rigid. So in batteries, there's a volume expansion happening for both anode and cathode. So they will form some void during the operation. So the interface is a seal of contact, and the compatibility is the biggest issue these days and is the bottleneck for the commercialization of lithium solid state batteries. But for sodium, it is still in the early stage, and ion conductivity is still we still need to develop a high ionic conductor for sodium solid state. So lithium, right now, is the interface is the bottleneck. Very good point. Thanks.
Okay, so thank you very much, Professor Su. It's very wonderful talk, and thank you very much. I believe it's very late over there in the US right now.
Yeah, okay, it's 10:30. Yes.
Okay, so thank you so much. Let's thank the speaker again.
Thank you.
Okay.